Hi everyone, welcome to this video. I just started making some videos about economic geology and the practical aspects of economic geology. I go through some reports, articles and reviews of different types of ore deposits. I just started with porphyry, copper and gold deposits, because they are my favorite type of ore deposits. This video is the first article, or a review of the first article published in a special publication of SEG, Economic Geology, which is a attribute to Dr. Jeremy Richards. So in this first chapter, I will summarize magmatic controls on metal endowments of porphyry, copper and gold deposits, written by Massimo Chiaradia. Okay, let's zoom out for a moment. This map shows the global distribution of the world's biggest porphyry, copper and gold deposits. Whether it's Chuquicamata in Chile or Grasberg in Indonesia, they all share one thing. They root in subduction related magmatism, and it's not just where they are, it's why they're located in those areas. In this panel, which is the figure number 2 of the article, we have a multi-panel plot, which is our geochemical roadmap to porphyry fertility. We have different diagrams for important elements: magnesium, iron, copper, and ratio of strontium yttrium, which is a very important ratio, and crust thickness. And we can see that in thicker crust, magmas evolve slowly under high pressure. That favors crystallization of magnetite and garnet, and those are minerals that pull out iron and keep sulfides from saturating too early. So what's the result? We have higher strontium and yttrium ratios, and Volta-rich magmas, which stick around long enough to build big deposits. So what's the sweet spot for fertility? We have intermediate magnesium or MgO. We have moderate Fe2O3, and we have strontium ratios between 50 and 150. That's a kind of roadmap or geochemical signature for most of the productive porphyry systems. Okay, here we have a simulation based on Monte Carlo method for generation of magmatic systems. We have duration of magma injection versus the pressure or depths, and we have water content in magma shown in white lines or dots. We have fertility of magma using strontium yttrium ratios in red in yellow lines, and here again we have a sweet spot around 13 kilometer depths or 4.4 or 0.4 gigapascal pressure. So at these depths, pressure is high enough to stabilize garnet and suppress plagioclase. That's an important chemical condition that keeps water and metals like copper, gold, and molybdenum trapped longer in the magma. And this relationship allows the magma to become more fertile and favorable to create mineral deposits. And also we have duration of magma injection as an important factor, and for duration of more than 2.5 million years. If magma keeps accumulating for a long time, it builds up more volume and retains more water, and overall it increases the total budget of water and metals. And these conditions overall would create large volta-rich magma chambers, and they're more likely to create economically favorable ore deposits. In this figure we have comparison between the pressure, copper content, and the water content of the magma, and also here what we have color coded different ratios of strontium yttrium. So when it comes to water, there's a general consensus that more water must be better, right? But not exactly. These plots show that the most fertile magmas are not the wettest. We have high contents of magmas here, and with very lower content of copper, and we have a window here with maybe 6 to 13% water content, which is a kind of window. And the important thing is that the most fertile systems are not the wettest. They are the ones that hold on to water long enough. And magmas that exhaust fluids too early, they would lose copper before reaching the Dior zone. And fertile magmas walk tightrope, rich in water, but they're still undersaturated. Here again we have copper content comparing to overall duration of or deposits or deposition. We have different deposits, and here we have color-coded depths of formation. And you can see that small porphyries are located on the left side of duration. And we have huge deposits here like El Teniente or Chuquicamata, which took much more time, actually the longest time in this time scale, to create those huge deposits. And this figure shows that the biggest copper deposits took millions of years to build, and of course they usually have multiple pulses. It's not one-shot eruption. It's a long simmering process with fluids being exhaled over time as the system matures and fractures open up to receive them. So what all this mean? What does all this mean for mineral exploration? Well, it depends on what we are looking for. We have different approaches or clues for copper-rich or gold-rich systems. For copper-rich systems, we need thick crust, thick continental crust, which provides pressure, needed for deep magma evolution, and it allows magma to differentiate slowly at depths, accumulating volatiles like water and keep sulfur within, solving them prematurely. And the results are large, water-rich, metal-charged magmas, which can create giant porphyry copper systems. And of course, we have long-lived compressional regimes. Those compression traps magma deep in the crust and allow it to evolve without escaping. Prolonged compression leads to repeated magma injection. They build up large reservoirs with high metal content, and finally these systems release fluids explosively into faults and fractures which form ore bodies. And also we need high strontium yttrium intrusive bodies, which is a kind of chemical signature for magmas producing porphyry copper deposits. And it shows that magmas formed under high pressure, where garnet is stable and plastic clays is suppressed, and it indicates deep differentiation and the potential to carry more water and volatiles, which are key for ore formation. And as I said, these are chemical fingerprint of fertile magmatic systems. And we have evidence of large-scale deep magmatic magma chambers, and at which large volumes of magma are needed to produce the amount of fluid and metal required for a significant deposit. And for the gold deposits, we have a quite different story. In opposite to copper-rich porphyries, we need post-subduction or extensional settings, and they often stretches those tectonic areas often stretches or relaxes after compression, and they allows magmas to rise quickly and shallowly without stalling or crystallizing too early. Those are the key points in gold porphyry deposits. And since gold stays in fluid longer and can be efficiently dumped at shallow crustal levels. And so we have shallow depths intrusions, and in terms of geochemistry, they're mostly alkaline, they're high in potassium and sodium, which are more likely to be enriched in gold and volatiles. And so those magmas tend to ascend repeatedly and evolve into the upper crust, and they create high-grade gold systems like Grasberg or Bingham Canyon. And they're short-lived, but because the in-play is quite close to surface at the shallow depths, we have intense magmatic hydrothermal episodes, and they have high impact and low footprint. Thanks for watching.